Hi, and welcome to our video. This is a presentation of the impact on body signals of smoking and drinking. It is a final presentation for Computer Science 240 data mining in the University of Rochester for 2023. I am Junhua Huang. This is the Yuyang Wang. This is the Yuesong Huang. This is the Boyang Wang. The motivation of our research is pretty simple. It's actually inspired by our personal experience. We're the team of smokers, drinkers, and non-users, and we're curious, how do those habits affect the health? We're trying to combine the personal experience with the core technique that we learn in the Computer Science 240 and expanding our personal perspective to the universal insights.
These are two highlighted literature that we took a look on. There are also other literatures that provide insightful attributes that how drinking and smoking do harm to human body and the society, which motivate us to do the research. Some literatures provide insightful attribute to the prediction, which informed us which variable is important for the model. These are the data sets that we have. And the data set is from Kaggle. We use these data sets have 1 million-ish observation that includes critical data points like age, height, weight, blood pressure, and some measures of health condition. Most attribute is easy to read, while these attributes need some explanation. So the first two is SBP and DBP. These are two blood pressures that indicate our heart. And the other four is SGOT-AST, SGOT-ALT, total, and also the gamma GTP. And these are important measures of heart and the liver that indicate our personal health condition. Within the variables, we found a lot of correlation. First is the strong correlation observation. And the strong correlation happened between LDL core and total. So this correlation is pretty strong, while we also have some medium correlation, which is between the height and the sex type. And also we have some hypotheses and goals. The first the goals is we want to find out the correlation between the lifestyle and the health condition. And also we want to infer somebody's drinking and smoking status based on their health condition. And then we want to assess the risk levels associated with smoking and drinking patterns. Last but not the least, we want to improve public health using advanced machine learning mechanisms.
And before we do the modeling, we're trying to do some data preprocessing and feature engineering. While our data set includes height and weight, those measurements alone does not fully reflect the individual's health, as ideal weight range vary with height. Therefore, we incorporate more precise feature, the body mass index, so-called BMI, based on the value of the weight and height in the observations. BMI is a standard way to evaluate whether a person's weight is healthily related to their height, calculated by dividing the weight in kilogram by height in meters squared. These figures more accurately reflect an individual's weight status. Unlike using height and weight alone, BMI accounts for the proportional relationship between the two, better revealing whether an individual is overweight or underweighted. This is closely linked to the personal lifestyle habits, like smoking and drinking. and it allows us to more accurately predict a personal health habit and risk. In our data analysis, we regard blood pressure, which include both diastolic and systolic pressure. It's a crucial indicator for cardiovascular health. By classifying blood pressure as a whole rather than analysis diastolic and systolic pressure independently, we enable more accurate identification of the health risk. This approach not only categorizes the data effectively, but also help in reduce the dimension of the dataset, making more manageable and interpretable.
This is the 8-power algorithm results with a minimum support of 0.2. We discover fascinating frequency item sets that uncover hidden patterns in our dataset. And notably, a support of 94% of urine protein being positive indicates a prevalent condition in our subjects. Smoking and drinking status appear equally distributed, each around the 50% mark, suggesting a balanced representation in our data. Interestingly, when we look at combined data sets, the correlation between no smoking status and urine protein positivity is significant. With a support of 57%, this could imply a health pattern worth investigating further. Gender also plays a role, with male subjects showing a higher occurrence of urine protein positivity. Meanwhile, combining gender, drinking and smoking status give us richer, more complex pattern with support level exceeding 30% in some cases.
And what's more, we also tried categorizing cholesterol ratio, vision impairment, spectrum, and k-means. We do the scaling using Minimax and standard scaler, and we do the PCA. As you can see, there are two graphs that are related to our approach.
Well, as for the most important part, the model. Like in this project, we use like two models and which like have a different some sort of features. And the first one we use is the SVM, the support vector machine. Well, like from our expect, like the SVM should be a robust and effective sort of like the classifier method, and we think like we can have a very good result from it. But there's something happened for us since like we're using a really huge data set which contains about like 1 million of the observations and about like the 70 columns as a feature, so that's increasing the complexity of the model. So that makes our SVM is very time consuming, and that is not reasonable and impractical. As our predictions, like to perform the full like grid search process, it takes about like more than a whole weeks to do that. That is impossible. But this is not a place to give up. To finish our first models, like we're using like two different methods. The first one is sort of like we're randomly selecting about like 1/10 of the data set to use for the training, which reduce the time to a practical scale about like 10 minutes, 20 minutes. And also like we're using even smaller data set to doing the grid search to infer possible like good configuration of the module and the parameters. And we sort of like in this process, it will give us a good result for the whole data for the whole module. And as for the result of the SVM, this is the training process that used about like 100,000 of the sample observations, and it turns out like the performance is good. Overall, like they have the accuracy of the 83%, and they give us a very good performance for both predicting the smoking and drinking. And well, since like it have the drawbacks, the time consumption, we trying to adopting another method to sort of like give a better performance, overall performance.
We try to search for a configuration on the smaller portion, and then our investigation into the health impacts of smoking and drinking using a high dimensional data set featuring over 17 variables has concluded. Advanced machine learning techniques have relevant that both XGB boost and the SVN are robust classifiers. XGB boost strike an excellent balance between speed and accuracy, whatever SVN, despite its higher precision, require more processing time. As we look ahead, we are excited to refine this model further, potentially integrating them into medical service application. As you can see, SGB Boost distinguished itself as not only a robust and highly efficiency classifier, but also a swift performer in our test. Even with the comprehensive real search CV hyperparameter tuning, the entire optimization process locked into an impressive 34 minutes. Its fusion of accuracy and particularly in execution time underscore XGB Boost's suitability of large-scale data analysis, optimizing its predictive accuracy for key health behavior like smoking and drinking. And as you can see about 34 minutes, about 70 minutes each, including grill search CV. Applying XGB Boost to the full data set, we observed significant results. For smoking status prediction, the model achieved an accuracy of 81% and an F1 score of 78%. Similarly, for drinking status, the accuracy was 73% with a F1 score of 73% also. These results demonstrate XGB Boost's ability to efficiently handle large data set and deliver reliable predictions. As a result, SVN outperforms SGB Boost in accuracy and F1 score for both smoking and drinking status predictions. XGB Boost is significantly faster than SVN, making more time-efficient option. There's a trade-off between accuracy and time efficiency, of course. SVN is more accuracy, but takes way longer, while SGB is very fast, but less accurate. Overall, we figure out that XGB Boost have a very acceptable scores and even close to SVN and the shortest escape time. And in conclusion, we established correlation and causality between lifestyle habits and health signal. We employed advanced predictive model techniques to accurately classify individuals based on their health signals and into smokers, non-smokers, drinker, or not. Furthermore, we assist the risk level associated with smoking and drinking patterns, focusing on the health markers. Our analysis has been a comprehensive exploration of smoking and drinking impacts on health. Employing advanced machine learning techniques, we have demonstrated that both SGB Boost and SVN are capable classifiers. With SGB Boost offering time efficiency and SVN provide higher accuracy. Look ahead, we aim to fine-tune these complex models even better accuracy.
So in future, if we have a better tuning or a complex model, we are pretty sure that we will have a better accuracy. And also, if we can pack up the classifier into an app, we can help have a better medical service. And we are more than welcome if you want to contribute to this project. Please fill out the following questionnaire. And also you can fill in the questionnaire by scanning the QR code on the right side. And we promise that your data will be collected anonymously and you will receive detailed prediction results. And all feedbacks and questions can go to this email. And these are the references that we used in this presentation.